Deep in the Great Lakes lies one of the world's most critical engineering choke points. It is a system of massive water elevators that prevents the North American industrial economy from grinding to a halt. Welcome to the Soo Locks. To understand their power, we must look at the geography. Lake Superior is the highest Great Lake, sitting 21 feet above Lake Huron. All that water rushes downhill through the St. Mary's River, creating impassable rapids. A 1,000-foot cargo freighter carrying 70,000 tons of iron ore cannot simply jump down a 21-foot step. Without a way to bypass these rapids, shipping between the lakes would be completely impossible. The solution is a slow-motion liquid elevator. The locks raise and lower giant ships, allowing them to step down or climb up this watery staircase safely, but the way they do this is what makes them truly legendary. Raising or lowering a massive freighter requires moving millions of gallons of water, yet the Soo Locks do not use a single water pump. The entire system is powered by a force that costs absolutely nothing: gravity. Because Lake Superior is higher than Lake Huron, the water naturally wants to flow downhill. By opening and closing specific valves, engineers direct this natural downhill flow to fill or empty the lock chambers. Imagine two buckets connected by a hose. One bucket sits on a table, representing Lake Superior, and the other is on the floor. Opening the valve forces water from the top bucket to flow down into the bottom bucket naturally. To move this water, the locks use massive tunnels called culverts, which run underneath and alongside the chambers. These tunnels are so large that a subway train could easily drive through them. Inside the culverts, massive steel butterfly valves act as giant faucets. When rotated open, they allow the water to rush through the tunnels. When closed, they block the flow, isolating the chamber. If all that water rushed in from one end, it would create a violent whirlpool that could smash the ship. Instead, the water enters and leaves through dozens of small ports distributed evenly along the chamber floor. Think of the chamber like a giant bathtub filling from hundreds of tiny holes in the bottom. Rather than a single faucet, the water rises smoothly, keeping your turbo perfectly stable and secure. At each end of the lock are double doors called miter gates. When closed, they form a V shape pointing upstream. This angle is a brilliant piece of structural engineering designed to handle high water pressure. As water from the high side presses against the gates, the force pushes the two doors tighter against each other and the concrete walls. The water itself acts as the locking mechanism, tightening the seal. Because of this pressure, the gates can only be opened when the water levels on both sides are perfectly equal. Trying to open them before they are equalized would require impossible amounts of mechanical force. Imagine trying to open a door that opens inward when a gale force wind is pushing against it from the outside. The harder the wind blows, the tighter it stays shut. You can only open it when the wind stops. Does a heavy ship require more water to lift than a light one? The answer is no. A 70,000-ton cargo freighter and a tiny kayak required the exact same amount of water to rise. According to Archimedes' principle, a floating ship displaces a volume of water equal to its own weight. When the ship enters, that displaced water overflows out of the chamber, keeping the total weight constant. Think of putting a towboat into a cup of water. When you pour more water in, both the water and the boat rise together. The boat does not resist the rising water, it simply rides it to the top. Geographically, the locks are the linchpin of the North American industrial supply chain. Iron ore mined in Minnesota is loaded onto freighters on Lake Superior, which must pass the locks to reach eastern steel mills. Around 80 to 90 million tons of cargo transit the locks annually. Iron ore is the dominant commodity, representing the vast majority of this tonnage and powering the steel manufacturing industry. The facility operates two active locks, the MacArthur Lock and the Poe Lock. However, only the Poe Lock is large enough to handle the massive 1,000-foot freighters that carry the bulk of the cargo. This creates a major vulnerability. Nearly 90% of the U.S. iron ore supply is entirely dependent on this single lock. If the Poe Lock fails, the entire steel supply chain stops. Despite the risk, the economic benefits are massive. Great Lakes shipping saves approximately $500,000 annually in transportation costs compared to moving the same cargo by rail or truck. A single 1,000-foot ship can carry the equivalent cargo of 700 rail cars or 2,800 semi-trucks, making water transit far more cost-effective and environmentally friendly. If the Poe Lock were to shut down for 6 months, the economic fallout would be catastrophic, causing up to 11 million jobs to be lost and hitting the US economy by over $0.00000. To eliminate this single point of failure, the U.S. Army Corps of Engineers is currently constructing a new pole-sized lock, scheduled for completion by 2030. It will secure the iron ore supply chain. This new lock is estimated to generate $700,000 per year in economic benefits, securing manufacturing and making sure the industrial economy is protected from sudden disruptions. The engineering of the Soo Locks is a testament to how simple natural forces, gravity, water pressure, and displacement can be harnessed to move millions of tons of heavy cargo. By working with nature instead of fighting it, engineers build a system that operates effortlessly. Passive gravity systems are highly reliable, easily outlasting complex mechanical pumps. Thank you for watching this episode of Layman's Field. We hope to keep bringing knowledge for everyone. Subscribe for more scientific and engineering insights.